by the processor. As we saw earlier, the method of presentation is of paramount importance, so we describe it right after the implementation. The assertion of the multicast group memberships a router has received can be done in various ways. The direct use of IGMP messages can instruct the node to report back the required information. An easier alternative is to query the groups using SNMP and particularly the Internet Group Management Protocol MIB. The IGMP MIB is very simple and the information we require is located in two tables. The first is the IGMP interface table, which simply lists all interfaces with IGMP enabled. But since it is typical to have all interfaces enabled for multicast, most of the time this table will simply report all interfaces on the machine. The second and most important table is the IGMP cache table, which is used to report the groups that have been subscribed to and to which interface each one of them. When a managed node indicates that there are subscribers attached to it for a specific group, it is reasonable to expect the distribution tree of that group to reach the node. Otherwise, there is some kind of problem in the network. One of the main functions of the weather map is the depiction of the topology of the multicast network. Although the topology can be discovered using the MIB2 subtree, a better and easier alternative is using the protocol-independent multicast MIB. The true multicast layer topology can be discovered by filtering out any links which are non-multicast or deactivated. The PIM MIB contains a list of all the PIM neighbors and their connecting interface. A complete tree representing the multicast topology can be constructed by retrieving this information from all the managed nodes and combining the results. Special care is taken regarding multi-access segments when there are more than two PIM neighbors present in the subnet. The knowledge of the links in the topology that are multicast enabled leads to the next step, which is to measure the traffic that flows through these links. In a similar way to the usage of the interfaces table from the MIB2, the interface table from the IP multicast routing MIB can supply the measurements. The links that were discovered in the previous step are queried, and the returned values represent the overall multicast traffic irrespective of group. MRTG or RRD tool can be used then to graph the values and provide a diagram. To provide a more fine-grained picture of the traffic, now we must limit the scope of our measurements to a specific group. The IP multicast routing MIB incorporates two tables that are useful to gather group-specific data. First, the multicast routing table has a line for each multicast source and group pair that is known. Second, there is a line in the next hop table of the same MIB for each neighboring node the source group pair must be forwarded. In other words, a router always knows all the active sources for each group and from where it expects packet of that group. Additionally, it also knows where to forward packets belonging to each individual pair. It is obvious that to calculate the amount of traffic that arrives to an interface and belongs to a specific group, one must add the counters from all the entries concerning the group and incoming interface. Furthermore, it is possible to associate each incoming interface with a PIM neighbor and construct a traffic matrix for the group in question. This matrix contains both the topology of the distribution tree for the group and the traffic for each of its branches. Traffic matrices for all groups can thus be constructed and combined in a cache file. This file will be usable directly by the presentation module. Now, we're going to have a brief look on the interface of the tool. There isn't a lot to say here. First, the visualization of overall traffic is is the picture on the right, which is accessed through a simple web browser from anywhere. As we see, the nodes, which are routers, are visible as geographic locations, and the links which are multicast enabled appear as arrows, as bidirectional arrows. The color reveals the amount of traffic flowing through each link. And if we are interested in a historical view of the traffic, we just hover the mouse over the link and we get a diagram for the last 24 hours. Now, additional information can be obtained by hovering the mouse over the node, any node. As we see, by hovering the mouse over the Xanthi node, we can see its IGMP memberships. This means which nodes have joined to receive groups directly attached to the Xanthi router. We can see the incoming and outgoing groups from its IP multicast routing MIB. Plus, we can see the MSDP cache size on the router. It is extremely easy to plug other pluggable modules to this mechanism and have other sorts of information readily available. Now, about the visualization of group-specific traffic. This works the same way as the overall multicast traffic, but before we get this picture, we select the group from a pull-down menu which is presented to us. Again, the nodes are visible as geographic locations, but now only the links which are carrying traffic which belongs to this specific multicast group are drawn. Again, color reveals the traffic flowing through the link. And now some conclusions. The mechanism of this tool is modular and thus extremely extensible. Any module can be rewritten without affecting the others. It is also possible to have many presentation modules all working in parallel and independent from each other. Since the data is exported in an intermediate cache file before drawing, storage of historical data can be implemented by saving various versions of the file with a time tag on them. Lastly, because it uses standardized MIBs, the tool can be used in the majority of today's multicast networks. One drawback is that the collection process of the raw data from the IP multicast routing MIB is time-consuming because the entire contents of the MIB have to be retrieved from all the managed nodes at regular intervals. And last, the advantages of the interface is that it is, okay, this is the last slide. It is independent from the instrumentation, which means we can replace it easily. The interface is actually quite snappy. It is very fast because it does not need to draw the information directly from the routers. Rather, it uses a cache file we mentioned earlier. We believe that this is an intuitive display of the refined data about the multicast traffic of the network. And I would also like to thank Panagiotis Christias for borrowing us the drawing functions for the multicast weather map. Okay, that will be all. Thank you very much.
Thank you very much for that. We have a few minutes left if anyone has any questions. One there.
I do have a few questions. First one is, can we retry this tool somewhere to test it or to deploy it? Is it possible I get the tool or is it private or channel?
No, we can, we give it away. But it's in an intermediate stage of development, but at some later point, not very far from today, we're going to release the source so everyone can test it and enhance it perhaps.
Any more questions?
I didn't say I use IGMP. I said it is possible to use IGMP to query the IGMP memberships on each node. But this is, in fact, this is the way I think the smart plugin of the HP OpenView uses to query the memberships. But we felt it is more appropriate to use a more uniform way to retrieve the data from the nodes. So we use SNMP for all of the functions. And we use the IGMP MIB to retrieve the IGMP memberships. That covers your question?
No. Why do you need IGMP? Why is IGMP interesting in code?
Because, because if there is an IGMP membership in one of the nodes, one of the routers on your network, and you see that the shared or the source tree does not reach this node, you can ascertain that there is some kind of trouble there. Because the tree should be reaching this node, because someone asked for one group, but it does not reach the end router. That answers your question?
I didn't really see why you have clients directly connected to the nodes. That's what. Usually,
There are some cases in which clients can be directly attached to Ethernet segments on the nodes.
Sounds as though you should both get together in the bar afterwards and discuss it in more detail. Thank you very much, Anathosius. I'd like to welcome our next speaker, but I'll let all these few people find seats. Our next talk is going to be on the high-speed programmable monitoring adapter, which is part of this session. And the speaker is Vladimir Schmotlar. He has worked several years as a Unix systems programmer, and he's actually been working with SESnet, which is the operator of the Czech network, for 8 years now. So I'm going to pass it over to Vladimir.
I have two problems to start this presentation.
Unix program, you should be able to do this. If we go back to there,
Okay, yes,
it's a bit confusing. Oops. There you are. Oops. Okay.
Thank you for the introduction. This presentation concerns Layer 3 monitoring at high-speed networks. For the monitoring at lower layers than L3, there are available a lot of analyzers, but Layer 3 monitoring is usually done by workstation with some networking adapter. There are two basic methods how to do this monitoring. The first one is real-time processing, which means that each packet is processed immediately when it comes to the system, and only results are stored on disk. The second method is offline processing, which means that all incoming traffic is at first stored in disk, and the processing is done later, maybe on some more powerful computer system. Such approach has limited scalability. The first method is limited by the CPU performance, as it is well known that in past time the performance of CPU has been increased not such rapidly as the network speed. And the second method is limited by disk system, mainly by disk systems, as it is not possible or not simple to store such huge amount of data at such a high rate. Even the throughput of local bus can limit both these methods. For instance, the sustained flow of offloaded 10 gigabit line gives more data than the throughput of PCIX at 64 bits, 133 megahertz. Therefore, some new methods, some new kind of adapters for monitoring is necessary. One solution of the problem are advanced intelligent adapters which are able to do some data preprocessing. These adapters usually have some functionalities. It is at first the ability to provide timestamps, as the precise timestamping is essential for many monitoring applications, for instance for one-way delay measurement. Windows. Yeah. Another functionality is the packet classification. In order we can process different data flows by different way, and the main usage of the classification is the elimination of background traffic. For this reason, as background traffic, we understand everything what is not part of our interest. Generally, the monitoring adapter should implement such kind of on-board processing in order to decrease the load of main CPU and to reduce the amount of stored data. The advanced method is to implement directly some monitoring algorithms, or at least some part of algorithms inside the adapter, and therefore the load of system is further decreased. Well, it was a theoretical viewpoint. Now back to reality. We can use for monitoring standard network in card, but such card has no onboard processing capability, and it is difficult to provide precise timestamping in this case, as timestamps are assigned by the driver, and the delay between the packet arrival time and the timestamp evaluation is not constant. And such cards are usable for speed up to 100 megabits, let's say fast internet, but it is rather difficult to use it for gigabit per second speed, and nearly impossible for higher speed. Another solution are well-known duck cards. You maybe know these cards. They are produced by the company NRENs. And when we are speaking about the Ethernet world, there are available duck cards of row 4. 4.1 has 2 channels, each 1 gigabit Ethernet. But this card doesn't offer any onboard processing. It is only evaluated at precise timestamp, and the amount of stored data is reduced by cutting only beginning part of the packet therefore it is possible to configure the card to store only headers of packet. For 10 gigabit Ethernet, there exists the version DAC6, which is able to do some onboard filtering of packets. In the rest part of this presentation, I will describe the Scampi adapter, and such kind of adapter is currently designed for speed up to 10 gigabit, and it is able to do filtering and advanced data processing. The Scampi adapter has been developed or is under development of the project Scampi. Scampi project is the project of IST family of fifth framework. The adapter is based on the universal programmable card Combo 6. This card was designed by CESNET and Masaryk University in our internal project, and therefore this presentation describes not only results of the Scampi team, but also of part of result of team developing this Combo 6 card. The Scampi adapter consists of 3 parts. It is the main board, the Combo 6 card. The main chip there is the FPGA Virtex 2, and the card contains also RAM modules and CAM memory for packet classification. There is a daughter card with link interfaces. Currently, in the scope of Scampi, we are using 1 gigabit Ethernet, and in phase of debugging is 10 gigabit Ethernet card. And the third part is the timestamp unit, which is currently realized as a separate PCI card. Here is the photo of this card. We can identify the Virtex chip, the RAM module, the CAM memory, and connectors for the daughter card with link interfaces. As you can see, the current version is only 32-bit PCI, but we intend to develop a 64-bit PCI card. In the scope of the Scampi project, we identified several kinds of monitoring applications in order to demonstrate the functionality of the Scampi adapter and the functionality of the universal monitoring API, which is developed in scope of the Scampi project 2. These applications are at first packet capturing. As a packet capturing, we understand not capturing of all the data flow, but only selected subsets of data flow are captured, and the rest of background traffic is dropped. Other family of applications are flow statistics. Such type of applications is very suitable for implementation in the similar kind of adapter, as it is possible to move the algorithm to the card and not to do it inside the host computer. Similar application is the verification of service level specification and cross parameters measurement. And the last kind of application which we are using in Scampi, or we are developing in Scampi project, is the identification of malicious data traffic, for instance, deny of service detection. In this picture is shown the simple structure of the adapter. I have to note that some of these blocks are represented by hardware, but some of them are firmware implemented inside the FPGA. I will describe it later. When the packet arrives to the card, it is immediately evaluated the timestamp, and packet is then processed in this classification unit. While the header of packet continues to these blocks that are designed for support of applications, the packet body or the payload of packet is stored in queue and waits here for the result of header processing in order to be dropped or to be stored in local memory, and later is the packet transferred to the host computer if it is desired. We have here these three blocks: that is statistical unit, sampling unit, and payload checker. I will describe them later. Well, the timestamp unit. A timestamp unit is based off 100 MHz clock. It seems to be really high frequency, but we need such kind of resolution. It represents the resolution of clock 10 nanosecond, as at the 10 gigabit line, packet with length of 64 bytes arrived every about 50 nanoseconds, and we need to assign unique timestamp to each packet. The timestamp is designed in the format similar to the format used in NTP. It is 64-bit long word. The first fixed point, the first half, represents the number of seconds since the time 0. In Unix word, it is November 1, 1970. The second part is the fraction of second, and therefore the precision of such representation is about 1/4 of nanosecond. The clock definitely has to be synchronized, and it is possible to do the synchronization by external PPS signal, pulse per second. Such signal is provided usually by GPS receiver, or it can be provided by atom clock also, if available. In the case of PPS synchronization, the accuracy of clock is in the order of 1 microsecond. When we are using NTP synchronization from some close NTP server, the accuracy is better than 100 microsecond. Typically 50 microsecond can be reached. In case there is no external synchronization available, we have free running oscillator, and the accuracy is done by the aging of quartz. Well, now I will describe VHDL blocks of the adapter. As you remember from the structure of adapter, there are the first two blocks, HFE and LUP, are together the classification unit. The first block is designed to extract the data from packet headers and to to construct a unified structure, head structure, which will be processed in further blocks. The second unit is the lookup processor, and this unit does the classification. It has two phases. The first phase is matching with CAM. It is standard method of classification. But in the second phase, there is a special programmable engine which is able to do comparison with several constants stored in memory. The engine is able to do up to 8 such instructions in the current design. The result of classification is a 32-word bit word which describes the further processing of the packet in the adapter. I have to note that these two blocks are designed as a special structure which are called by authors nanoprocessors, and in the presentation tomorrow afternoon in the MOMS section, my colleague Jura Novotný will describe the hardware of adapter and this part probably more deeply. The sampling unit is the first of the unit to support applications. Sampling unit is designed to decrease the data flow, and it is able to do both deterministic sampling and probabilistic sampling. Deterministic sampling means that each nth packet is passing through the unit, the other packets are dropped. Probabilistic sampling means that the packet is passing with the probability 1 over n. Another two blocks for application support are a payload checker and statistic unit. Payload checker is able to inspect the payload of packet and to find a set of patterns inside the payload. The current design is limited by the CAM word width, and it is possible to find patterns up to 16 bytes. The CAM also limits the number of such patterns, and it is currently about 200 such patterns. It is possible to aggregate patterns into group, and therefore only some group of patterns is checked in the particular packet according to the result of classification. And the last unit is the statistic unit. It has two parts. It is statistic based on the packet lengths, and this unit is able to store number of packets, the total length of packet, or the sum of packet lengths, the sum of squares of packet lengths, and the minimal and maximal value of the lengths. Similarly, there is a part based on on intervals between subsequent packets, and it stores the number of packets, total time, it means the accumulated time between the first and last packet, the sum of squares of these intervals, and also both minimal and maximal value. From these data we can simply calculate more interested statistics. It is for packet length, it is the average data rate, the average length of packet, the variation of the packet length, and for the time part, it is the total time of data flow and the average interpacket interval and its variation. Yeah, to have some conclusion, I think that by design of the Scampi adapter, we approved that the specialized adapter in workstation is suitable solution for monitoring for speed 10 gigabit per second, and we believe that such solution is scalable and therefore is suitable for higher speed also. And another result is that FPGA is a suitable platform for support of monitoring applications. It is the last slide. Thank you for your attention.
We still have some time for questions, so have you got any questions for Vladimir?
Okay.
One right at the back.
Yes, what would be the difference of what you did with the standard whatever in a network processor?
Yeah, it was the strategic decision not to use network processor but to use FPGA. It was a long time of discussion what is better to use, but we decided to base in the Scampi project our adapters on FPGA.
And the reason?
It is, how to say it, it's rather, the reason was mainly some bad experiences of when our colleagues in past time tried to use network processors. It was really complicated to buy these processors, and the producers of network processors used to change it very rapidly, and it was nearly impossible to develop something and to do it not in the case of some massive production, but in the case of a research project.
Question?
The period of the innovation was too high for our purpose.
Question at the front.
Does the way in which you configure the card have an impact on its performance? So if you're trying to take certain statistics out of the card, does that change the performance that you could get from it? And also, you mentioned that the approach was scalable. Could you say something?
DAC card for 1 gigabit Ethernet, there is only timestamping unit, and it is only possible to cut the length of packet, and no other preprocessing of data. Therefore, I think that this definitely our design is newer, and I think that more advanced. What I know about the 10 gigabit DAC card, it is able to do filtering, but for me are not available more data about it. In any way, we plan to compare this card with DAC card 1 gigabit next month. We are arranging some tests just now.
Final question at the back.
Sorry? It is under development. Currently, there are two problems generally, two approaches. The one is the 10 gigabit daughter card. The second one is the parallel structure inside the Combo 6 card. The daughter card has been developed and it works. And I am not sure exactly if it is possible to do filtering at 10 gigabits.
Thank you very much, Vladimir. Our third and final speaker this afternoon comes from the University of Seville in Spain. His research deals with network quality of service and congestion control, as well as fuzzy interference system. He's currently actively involved in a number of free software projects, mostly in the field of multimedia, voice over IP and real-time conferencing systems. So I'd like to welcome Federico Montesino.
Now, good afternoon. This presentation will deal with active network measurement, with active bandwidth estimation tools, and what challenges we find when using them in high-performance networks. It will comprise 3 sections. First, we'll see an introduction on active bandwidth estimation tools. Then we will present an evaluation framework that has been developed to perform an assessment or a comparative analysis of active bandwidth estimation tools. And finally, we will summarize some results, conclusions, and some comments on expected work for the future. When we talk about active measurement tools, we are dealing with tools that work end-to-end and that try to infer path properties from the reaction of probe packets. The idea is to inject packets in the network and to observe the behavior of these packets. The most simple case, perhaps, for an active measurement tool is ping, is the most simple case. This kind of measurement tools shows advantages such as that they are accessible for end users and have lower requirements when compared with passive measurement, as was the case with Scampi, for instance, in the previous presentation. We don't need special hardware, in principle, and we don't need access to important or core nodes in the network. We have an end user's perspective, and we can deploy distributed infrastructures for active measurement. However, these tools present some drawbacks derived from how they work. They require a good model or for the dynamics of packet traffics, and they are also sensitive to measurement errors, an issue which is now becoming more and more important with optical networks. Well, look that we have talked about the active measurement tools, and now we focus on active bandwidth estimation tools, because we don't have, in the current internet, we don't have a way to measure bandwidth. We have to estimate bandwidth metrics from measurements. And the need for this kind of tools has been around for about 10 years. In 1996, we find the first case of bandwidth estimation tool developed to support higher levels, in particular to support the dynamic selection of servers. From that time, there has been a proliferation of active bandwidth estimation tools, but at the same time that basic research was conducted on this topic. So when we look at the set of bandwidth estimation tools available, which is a quite wide set of tools, we find a lot of differences and disparities in terminology, and we find many different techniques and implementations. But in this presentation, we will talk of what have become the three standard bandwidth metrics, to better know what we refer to when we talk about bandwidth. We talk about capacity, which is a property of a path. Usually is an static property, but not always. If you are using, for instance, the wireless network, you will have a variable capacity. You can have 11 megabits, you can have 2 megabits. We also have available bandwidth, which is the portion of capacity which is unused. And now available bandwidth is not a path property. It's not just a path property. It's a condition that applies for an application at a given time and at a given time scale. Finally, if we look at the performance of TCP-based applications, we will look at the bulk transfer capacity, which is the achievable bandwidth usage with a TCP flow that follows the standard congestion and flow control mechanisms in TCP. So we currently can find many active measurement initiatives all around the world. Perhaps the most applicable here are some initiatives that were at NRENs some time ago, and at present Dante is deploying an active measurement infrastructures based on dedicated boxes, the test traffic measurement boxes. But most of these initiatives deal with other metrics that could be considered simpler in general, such as the one listed here. When we look at bandwidth, we find that we are not sure yet if we can trust the bandwidth measurements that estimations that we get with current tools. We find that we have a lot of techniques and tools. We could talk about around 30 tools publicly available, 30 open source tools that can be studied and compared and freely used in any network. And some new applications, some new emergent applications in current high-performance networks are starting to look at bandwidth estimation tools as a way to provide a bandwidth estimation service for applications. Particularly, grid systems are starting to use some of these tools, but in general, these tools can also be used in coordination with passive methods for network operation, can allow higher levels and particular application level to perform some functions such as congestion control or quality of service. They are also particularly interesting to provide a somewhat standard or formalized procedure of checking service level agreements. And finally, they have been and are expected to be a good way to improve our understanding of how the dynamics of the traffic of packets in the internet is. So let's start with the description of the evaluation framework we have developed, and we will start with the motivations. So, as we've seen, bandwidth estimation has become a complex and under development problem, and we came up with the question that if we can consider current bandwidth estimation techniques and tools a reliable basis for providing a bandwidth estimation service, and also how far can we reach with current estimation tools. What we look at with this framework is to provide a systematic approach to the performance evaluation of these tools, so that we can answer this question now and with future higher performance networks, as a general design intention. We have developed a set, basically what our evaluation framework is a set of scripts and helper tools for integration and analysis of the results of bandwidth estimation tools. And it has been designed so that we can perform a comparative analysis of tools with a well-established set of practices and procedures, and for analyzing at the same time the three metrics aforementioned. We have tried to consider a wide subset of active bandwidth estimation tools to take advantage of the many techniques and different implementations available. And we have established also a set of numerical comparison criteria with the aim at allowing the evaluation of these tools from a numerical and a statistical point of view, and also from other higher level decision-making systems. So, a very broad description of the scenarios and tools in this slide. We have done tests with a wide number of tests with these tools, mostly in the backbone of the Spanish NREN, and also in connections in current GIANT. and compare some results with the results we get in other kind of mostly private networks. Well, you have here the table of tools that have been that are being tested, and to better know what we are talking about when we say we are assessing and comparing tools, we see here the list of comparison criteria we have followed to compare tools. Apart from a basic set of properties that establishes a taxonomy of tools, we have considered the consistency of the estimates provided by the tools, the accuracy, and also the intrusiveness. An important issue with these tools is that they can provide a good estimate of bandwidth without really using bandwidth, just with as few as possible probe packets. And also also considered the time required to provide estimation and how much time is required to provide a certain level of accuracy, and also the dependence of these parameters and properties of the network and the host which is performing the measurement. Usually these tools have been employed and have been designed to be used in any host, in commodity hardware, and you can run them as if you ran traceroute or ping or whatever simple measurement tool. So our evaluation software includes components for functions such as automation, classification, and post-processing of results. It's a low-level framework. It's not targeted at users. It's targeted at most as to researchers and network operators who have an understanding of how these tools work. It is implemented in scripts in Ruby language, and perhaps the most novel approach in this framework is that we have considered the huge amount of data you can record with just a few boxes distributed throughout the network. So we have considered some metadata for the experiments performed, many information so that we can do post-processing of the tests offline, considering a wide set of experiments and in a format that can be interchanged between the different operators or different researchers. For mathematical analysis, we also include some scripts in the TAFE, and some earlier versions have been available from the point in the last line of the slide. And really soon, the next week, or perhaps the next one, we will release a new improved version with a new remodeled web. We get to the results and conclusions. First, before talking about the conclusions from the results of the experiments, I summarize here in this slide some conclusions about interfaces, both user and programming interfaces, and formats for the recording of results of these tools, which are becoming more and more important, because we are talking of tools which will finally be used in a very distributed environment in grid systems. So we need some kind of format that eases the development of measurement servers and clients which can query and answer each other about the bandwidth state of the network. We summarize in this slide some overall limitations we have found in these tools. In the next slide, we will give a more concrete description of some of them. First, the system performance and load can have a deep impact, and specifically, when we say system performance, we refer mostly to I/O, input-output buses speed, and time stamping. There are some solutions being proposed which are based on specific dedicated hardware added to NICs. We also find some limitations due to the model that the tool follows. As we've said in one of the first slides, some of them can be overcome, some of them cannot. And that depends on what tool you use and what metric you are trying to use to estimate. We have found some infrastructural limitations that affect many of the current emergent technologies. Mostly firewalls and NAT affect this technology as well as multimedia systems. And also, we have found that these tools, we don't currently have good models for coping with the traffic shapers and QoS based services. Well, some more concrete results we summarize here. Generally speaking, it's hard to compare this tool. That's one of the reasons we have developed the evaluation framework, because we have many implementations and even more, we have many techniques and even more implementations. So many times you find important differences in estimates and important failures due to very small implementation details. However, summing the results, we can say that up to 100 megabits, perhaps something more, it can be. Currently, we can achieve a good accuracy. We will talk about consistency a bit later. But when we reach gigabyte speeds, or 2.5 gigabytes or 10 gigabytes, we need better hardware, and system and a dedicated system which is not interrupted in the measurement tasks. And at these speeds, we also find that the consistency of the estimates provided by these tools decreases roughly linearly. And that is in the best case, in the tools that employ techniques are implemented in such a way that doesn't break when the speed gets up. One punctual conclusion is that some of the tools can provide a good estimate according to some criteria, such as SPROF, that can provide capacity in a fast way, but usually the best approach is to combine different estimation techniques and tools to be able to provide different levels of accuracy and consistency in an increasing time window. I can summarize here the last point. That's just some particular cases of some kind of tools being more greedy of bandwidth than others, and some estimation techniques such as VPS being limited for high performance networks. So we get to conclusions. As a general conclusion, we have presented the aforementioned framework, we have highlighted the need for common user interface, formats, and application programming interfaces. And this is the good moment to start promoting initiatives from communities interested in using bandwidth estimation tools to get to an agreement in terminology and interfaces. As a general conclusion, we draw that with current optical technologies, the network capacity, the network performance is currently improving faster than estimation tools, and that if we need to accurately estimate bandwidth in current high performance networks, we necessarily have to use dedicated hardware and specific hardware, so we are somewhat losing one of the advantages of active measurement, and we have highlight some known limitations. For the near future, we expect to release a new version of the software, and to finish some system for classification and storage of results, so that the research in this direction can be continued with this distributed equipment and cooperative work. And for the last point, we comment the possible need to define the benchmarks for active bandwidth estimation tools, the same way as some entities such as the IATF is defining bandwidth, benchmarks for network performance. So I think that's all. Thank you for your attention.
Thank you, Federico. Have we got any questions? We've got a few minutes left. One at the front.
When you're saying whether a tool manages to measure the available bandwidth well or not, how do you know what the available bandwidth is?
This is a very good question, because available bandwidth, if you try to measure capacity, you usually have or can ask someone who tells you which is the real capacity of a path. But available bandwidth is a dynamic property of the path. It depends on the end of the connection. So there are some tricks to approach the real value of available bandwidth, if there is a real bandwidth, a real value. You can use some passive measurement tools. It is most people use MRTG. I don't know, a passive measurement tool that provides you the current bandwidth usage in a link, and you can compare these results with the results of the active. You can use path rate, for instance, from your box. The administrator of your network use MRTG to monitor the network, and you compare the two values. You can also take BTC and capacity as upper and lower limits for available bandwidth. And you can also do other tricks, such as using a number of boxes distributed throughout a network that you know how is arranged, and compare one measurement with the another. But providing a numerical comparison of available bandwidth estimation is not straightforward. And you basically don't know what's the available bandwidth. It's an approximation. Sorry, I can't hear you. I have used some emulated scenarios with some emulation tools such as NISNet or DumiNet, but for high performance of the level of gigabytes and 10 gigabytes, I've tested with the links of Rediris with the main points in the end, with France, Germany, Italy, the main currently 10 gigabytes links in the end.
One final question right at the end, and there is a microphone next to you now.
Hello. Your results, your experiment is very interesting and could be very useful for us. Where can we find detailed summary of your results? Is it available somewhere?
It should be available in a few days when the web. I gave a pointer over here. It should be available in a few days, a more detailed report. There is also another publication from this work, but not so much targeted at high-performance networks. I can comment later with you some other pointers, some other papers published on this work. And from this pointer, you can get some descriptions of the tools, a report on non-development report with detailed tests, and in the future steps I have commented the classification and storage system. The need for this system became visible when I started to put some test results available on the web, and it quickly became unmanageable. You came up having gigabytes and gigabytes of data, and it's not really too useful to have an exhaustive record of all your tests. What you need is to have a comfortable framework to perform tests that allows you to repeat the tests you are doing. So that's what I am working on now, the classification and storage system that this is searches and classification of tests. Because once you start doing more than a few tests, you get such a huge amount of tests and data that it becomes impossible to analyze and to compare. You can compare only a few estimates or a few tools between them, and then you start to need some other higher level techniques, which I briefly commented too. Sorry. When I say here numeric statistical, also it says fuzzy logic, neural networks, some computer intelligence of soft computing techniques that can be useful for a higher level comparison of results.
Okay, thank you very much, Federico. Can I thank all our speakers this afternoon? They've all given very interesting presentations, and just as importantly, they've all kept to time. They're all available, I believe, for the rest of the conference, so if you want to ask them more detailed questions, then I'm sure they'll appreciate a drink bought in the bar later. So thank you very much to all our speakers. Before you all go, can I remind you the coaches go back to the hotels at 6, and there will be schedules in each of your hotels to say when they're coming back for the welcome reception this evening. And thank you very much.